we're going to open this up to a general discussion. So you can still ask Norbert questions, but you can also ask all of the previous authors questions as well.
I had a question for Norbert. Great talk, Norbert. Fascinating mechanism. I think you might have mentioned this and maybe I just missed it or forgot, but can you remind me what is the source of those water molecules for this pumping process? Like, is this ice ablating elsewhere on the moon?
Yeah, it can be any source, right? But you ought to for the subsurface cold trapping to be efficient, ought to be sort of a regular source. It just can't be a single large impact or something. But I mean, Lati is evidence for water release, right? So of whatever original source. So it could be any source, but there are obviously even in the last 2 billion years there are sources. Some sources. I think the only question is how big a source, but there are sources.
Mm-hmm. Yeah, cool. Thanks.
Like solar wind generation, for example, right?
All right. We also had a question from earlier online. That was Michael Poston to Ross Potter. What temperatures does the ejecta reach?
Yes. So in our modeling, we paid more attention to the peak shock pressures. This is because these tend to give a better idea of the points at which material is likely to be melted or vaporized. So this isn't something we've done yet with the analysis. That's the next step that we are looking to. But yeah, we would analyze or focus on looking at the peak shock pressures to determine kind of the state of the ice material. Temperatures are interesting to look at just in terms of a general sense. But yeah, in terms of looking at the state of the material, we would focus on the peak shock pressures.
All right, great. Back to in-room question.
Hi, this is Dana Hurley. This is for Ross. Those are interesting simulations you're doing, and I was wondering if, instead of kilometer scale things, you were doing meter scale impacts into, meter scale ice. Would it look the same?
I'm not sure. I've only really ever dealt with sort of kilometer scale impacts myself. And given the potential change in the properties of the material in sort of the upper few centimeters, that might be more difficult to model and understand. But I think that's something that could be interesting to look at sort of as models become more versatile in their sort of computational power. But at the moment, that's not something I've considered, but it could be different results.
All right, thanks.
We have 9 more minutes for discussion, so plenty of time. All questions are good questions. Yeah, I know John always needs encouragement.
This is for Norbert. So on the timescales that you're talking about, obviously there are a lot of other things going on. So impact gardening is taking place, and have you, or are you thinking about how that affects your models? I understand it's like a meter per billion years of material removal and that sort of thing.
Yeah, I haven't studied this. No, I am although it clearly interacts at some point. No, I am thinking that for an impact to reach deeper than 10 centimeter, it doesn't happen very often, right? So I think it's too slow to interfere really with the migration downward. Now, eventually it will excavate some of the ice, but even that wouldn't probably not erase the ice. So I have not studied it, but I'm thinking it's probably too slow and too harmless to be a first order effect. But it mixes it at some point. It must mix it at some point. Yeah.
Thank you.
I have a question for Valentin. So it's really nice to see that. I'll just praise you until you get to the mic. It's really nice to see the Horus results. Is there a way to extract topography from those that's higher resolution than Lola, or is that a bit of a stretch?
It's quite a stretch. So we are trying that, but it's difficult for many reasons. But we are on it. So thanks for asking. This is
Yeah, the volatiles are falling from the sky today.
This is Wesley Chambers at Marshall. I have another question about the Horus data. I think to follow up on the earlier question, I think about geotechnical properties, what more, just kind of open-ended, what more, if anything, can we learn, or are you trying to learn about the Regulus geotechnical properties, or have you considered that with respect to NPSRs from that data?
That's a great question. I think the one thing is bearing capacity. So using voltage racks, for example, that's a classic. Maybe friction angle, also using voltage racks. And you might learn something when by looking at mass wasting, like granular flows, for example, runout length, for example, when compared to sunlit flows, flows in sunlit terrain, for example. So those are the kinds of things that I would think are interesting to look at in those images. So we haven't found only a handful of them so far, but we are on it. So there's more work to be done for sure.
I have a quick one for Margaret. Hey. So Margaret, if you had high resolution temperature maps for, say, the Viper landing site from a thermal model or something, then could you extend what you're doing to smaller scales? Have you thought about doing that?
Yeah, we've thought about it. Part of the work then turns into what Paul Hain and collaborators have been doing with micro cold traps. I think what would be really interesting is looking at the tens of meter scale, because we know there's going to be this transition zone between what Diviner sees versus what the like handheld, like if you put down your rock hammer, that scale for micro cold traps. So I think looking at that bridge size range would be really interesting. So yeah, we could definitely do that with Diviner, or not with Diviner, with Viper and the resulting thermal models. And I mean, there's no new fundamental physics, but I think it'd be really interesting to see what kind of processes from a geologic perspective you'd need to be able to do that. And as I've kind of been sitting over there mulling it over too, I think we have a fundamental problem where we can definitely get volatiles over the surface as per like the talks earlier today, but then burying them in enough time before they're destroyed or that how the destruction rate plays out, I think is a really key issue that I should probably also talk to Norbert about at some point. But yeah, I think that's something in terms of exploration, if we can get more data that addresses that issue, it'd be really cool. Hopefully that answers your question and wasn't too ranty.
Okay. So there's been a lot of discussion in the chat between Norbert and Michael. Perhaps Norbert could summarize some of that so everyone can hear about it.
Oh, we were just talking about what absorption model to use for quantifying residence times. I mean, the underlying issue is that lunar grains are very complicated, complex, amorphosized surfaces, right? How do you really know what the residence time is of water molecules? And in my case, I was dealing with ice and fairly humid regions, and so I think I parameterized that. but the drier the grain is, the more difficult it is to quantify with residence times. And that's something we still have to do as a community, both with experiments and theory. But yeah, there's two ways. One is you measure, the activation energy with a thermal desorption, or you use a measured isotherm Luna grain to quantify this residence times.
Cool. Thank you for sharing with the class. All right. Are there any other questions?
We have 2 more minutes, so time for a quick question.
Well, I'll make a comment. So argon is not thermally stable over geological times, but there's a large source of argon, and therefore I would expect a lot of argon mixed in with everything in these coal traps. And does that affect any of the results when you're considering whether it's sulfur or water or other things? Because argon may be taking up locations and filling in spots that other atoms are not able to reside there.
Yeah, so the argon transport problem is a very interesting problem. I haven't quite caught up to speed on what the newest solution is, but as a macroscopic phase, as a solid phase, argon will not condense.
All right, that brings us to the end of our discussion session. Let's give our presenters one more round of applause.